Let us now study about an AC circuit containing a resistor, an inductor and a capacitor in series. Okay, we say series RLC circuit. Let's see the picture here. Earlier we learned about this AC circuit containing only resistor. Okay, then we learned about only inductor. Then we learned only about capacitor. Now we're going to join all the three things and then we'll get a circuit. Okay, it has a resistor, inductor and a capacitor. Three things are there. So let's see this now. So we have a resistor here. Okay, this resistor is R, and then we have a coil here. This is a coil, that's L, and then you also have a capacitor, that is C. Okay, so we have these rings here. Okay, they are connected here to a AC circuit here, alternating current here. Okay, this is a resistor, that is R. Okay. This is the inductor, that is L, and this is a capacitor, that is C. Okay, so this is a circuit here. Okay, so we see RLC circuit. Some of them say LCR circuit also. LC then RLC circuit. Okay, this is a very important circuit. Okay, why? Because see, nowadays we use cell phones. Okay, see, actually there are many cell phone waves are coming there. Okay, but how does each cell phone gets one wave? Okay, or let's take a more simple example. For example, I'll take a radio here. Okay, now I have a radio. You can see there's a small radio here. Okay, now this radio has many stations there. Okay, so it has a FM, medium wave and short wave also. Okay, there will be thousands of stations, radio stations. Okay, we can select any one station by turning this knob here. Okay, this is an old one only. Okay, so by turning the knob we can adjust this and we can get the proper station. Okay, for example, FM stations are there. There may be 5 or 6 stations. Okay, and in that we have to select only one by turning the knob. Okay, so when you turn the knob, inside there is a capacitor here. The same circuit is there. Okay, so it may be a series circuit or a parallel LCR circuit may be inside that. Okay, so parallel circuit we will study in higher levels. Okay, now we are learning series LCR circuit. Okay, so there is a capacitor here in this thing. Okay, connected to the knob. So if you turn this knob, the capacitor will be changed. The value of capacitor is changed. Okay, we say variable capacitor, and then we can select the proper station. Okay, so this circuit is a very important circuit used in the radios, TVs, okay, and other devices. Okay, so now I have another radio here. Okay, this radio, if you see the scan button here. Okay, if you press the scan button, it will scan digitally, automatically scan. Okay, you see in your TV also we have the remotes there. Okay, or in DDH we have the remote. So when you press the remote, what happens? Remote button, the channel will change now. Okay, because it will select the different frequencies. Okay, so this LCR circuit is used in the radio circuits to get the proper wave there. Okay, there may be millions of stations there or thousands of stations there. Okay, out of that you have select only one station. Okay, that station is got by the circuit here. Okay, so this finds very useful in radio receivers. Okay, radio receivers, TV receivers, cell phone receivers. Okay, so this is of very great importance. Okay, now let's go with the topic here. Okay, now that we know the use here. Okay, so let's see. Now we give a voltage to that. Okay, the applied voltage is V is equal to Vm sine omega t. Okay, that is always we know. Okay, this is applied voltage. Okay, this is sine wave. Now you see, when you give the voltage here, the voltage divided across the three components here. The voltage across the resistor we write as VR. Okay, the voltage across the inductor we write as VL. The voltage across the inductor, that is VL, and the voltage across the capacitor we write as VC. Okay, so we have these three voltages. Okay, now let us construct a phasor diagram for this. Okay, so let's see a phasor diagram for this here. Okay, so let me draw the phasor diagram on the right side. Okay. So you need some space here. So this is a phasor diagram. I've drawn a very big one. Okay, also let me draw it up to here. Okay, where is this? I'll draw up to here. Okay, because we must write some things here. And using the phasor diagram only, we want to understand the concepts here. So phasor means what? It's a rotating vector. Okay, now we learned that first, if you have only resistor, let's see this first circuit here. Okay, imagine that we have only a resistor. We learned it already. Okay, and we see the current is like this way. Imagine this thing for current here. This is a phasor for the current here, I. Okay, and the current and the voltage will be in the same phase. Okay, so this will be the voltage here, VR. So current and voltage are in the same phase here. Okay, next you take the inductor here. Okay, so first I'll write here this one. So VR, that means the voltage across resistor is in phase. Okay, I don't have space here. Let me write down. Okay, I need some more space here to write. Okay, so I'll write here down. VR is in phase with current I. Okay, with the current I here. Okay, I means current. Okay. Next we see the voltage across the inductor. Okay, imagine that we have a circuit which contains only inductor. Okay, in that if you see the voltage across the inductor, it will lead this voltage, okay, current by pi by 2. Okay, let me choose another color here and write it down in this way. So this will be the voltage across the inductor, that is VL. It is more by how much? It's more by pi by 2, that is 90 degrees. Okay, so we can write as this way: the voltage across the inductor leads current I by pi by 2, that is 90 degrees. It is more by 90 degrees. Okay, and the third one we see a capacitor also is there. Okay, the voltage across the capacitor, it lags behind I by pi by 2. Okay, so that will choose another color here, this color. I'll choose another one, red I'll use it. So the voltage across the capacitor, this one, voltage across the capacitor, it is behind this current by pi by 2. Okay, that is 90 degrees here. Okay, so that will write here. So voltage across the capacitor lags behind. Okay, lags behind the current by pi by 2. Okay, this is very, very important. So you must know the phasor diagram first, how it comes, then we can understand the rest of the concepts. Very, very simple. Okay, now let me erase this things here. The heading I erase and this picture I erase here. Okay, picture may, okay, let me erase now. Okay, and we are going to use this phasor diagram and then derive this. Okay, but the picture is very, very important. This is used for the radio circuits there. Okay, now I erase this left side. Okay, I erase the left side. Now let's name this part. See, this part is O. Okay, the origin is O, and this one I'll name it as I. Okay, this one I'll name it as A. This one I'll name it as B, and this is named as C. Okay, so OI means the current vector here. Okay, the current phase in this case. Okay, so let's write this down. That's OI, that's equal to the maximum value of the current, that is IM. Okay, remember the phase value shows the maximum value. Okay, next we see this OA. Okay, OA means what? See, OA means it's the this one, that is the voltage across resistor here. Okay, VR. Okay, so voltage across resistor. Okay, if you see, I will draw it with a different color also from here to here. Okay, this is voltage across the resistor. Okay, so voltage across resistor and the current are in phase. Okay, that's what it is. Let me erase these things so that right let's make closer. Okay, so this is OA right here again. That's equal to what you must find. Okay, OA is equal to VR we know. Okay, that's the voltage across resistor. But we use Ohm's law here. Okay, using Ohm's law. Okay, that is what we know. V is equal to I into R. That I'm going to use here. Okay, let me erase this. OA is equal to VR. Okay, let me write VR itself. Okay, VR means what? Voltage across the resistor. Okay, that will be equal to this IM into R. Okay, I'm using same one. That is the Ohm's law formula. That is IM. Okay, that's the maximum current into the resistance. Okay, that's VR. Next we see OB. What's the value of OB equal to? OB, that means this VL. Okay, the voltage across the inductor, that will be equal to, again use Ohm's law, that is IM, okay, into R. Okay, instead of R, what happens is this inductor part now. Okay, inductor has inductive reactance. Inductive reactance is like the resistance. Okay, we say reactance. It's not resistance, it we say reactance. Okay, that is XL. We learned this earlier. Now OC, that means the voltage across the capacitor, that is VC here. Okay, that will be equal to IM into the capacitive reactance, that is XC. Okay, we learned earlier capacitive reactance, we learned this. Okay, so now we know these things. Now let's consider if the voltage across the inductor is more than the voltage across the capacitor. Okay, so if this is more than this one, what will happen? Okay, so if VL is more than the voltage of across the capacitor, voltage across the inductor is more than the voltage across the capacitor, then what will happen? Okay, so let's see this now. Voltage drop across the LC combination is VL minus VC. Okay, see now what happens is this part. Okay, this is minus now. This VC goes down, VL goes up here. So VL is better. Okay, so what happens? They will subtract now. Okay, that part I'll draw here. Okay, this one is a subtraction part here. That will be how much it is, VL minus VC. Can you understand this now? VL is upward, VC is minus, downwards. Okay, you bring it here, it will become less only now. This part is cut down. Okay, the length here VC will be cut here this side. So this part will be VL minus VC because they are in opposite directions. Okay, so you can say the voltage drop. Okay, the voltage drop across the LC combination. Okay, across the LC, that means what, inductor capacitor combination, is what it is. It is this one, that is VL minus VC. VL minus VC. Okay, this is the voltage drop. Okay, that one we can name it as, this one we marked O, no, this we wrote up to C, then we'll name it as D here, this end of the phasor. Okay, that will be equal to how much it is, O D vector. That's the phasor here. Okay, now we see that we are going to use this parallel law. Okay, I'm going to take this picture and we're going to use the parallel law. Okay, so let's write this down. Okay, for that what I'll do now, I'll erase this portion here on the left side. Okay, and then we will see how to use a parallel law in this picture here. So let us use the parallel law and then we'll see this now. Now I'm going to take this VL minus VC and this VR here. Okay, and using these two I'm going to draw the parallelogram. Let's see how to draw that. I'll draw separately also. Okay, first let's see this in the graph here. So now I put dot lines from this thing OD, okay, vector, then up to here, then I put another line here. So I construct a parallelogram. Okay, and this one will give us the resultant vector here. Okay, the resultant voltage, that is we write as VM V. Okay, so that's the resultant voltage here. Okay, let me write down. So using parallelogram law, okay, parallelogram law, using parallelogram law, what happens here? Okay, OE, this point, there is O, and this point will named as E also now. Okay, we marked up D now. This point will marked as E. Okay, using parallelogram law, OE vector, okay, it gives us the resultant voltage. Okay, OE gives us the resultant voltage. Gives the resultant voltage. Okay, so we know using vectors we learned in 11th standard. Okay, this parallel law, this will be the resultant. Okay, gives the resultant voltage in this case, voltage here. Okay, of the VR of these two things, that is of VR and VL minus VC. Okay, of VR and VL minus VC. Okay, be very careful. VL and VC should not look same. They should look different here. Okay, while writing this, okay, make distinction between L and C. Okay, and you see the length of this thing. Okay, the length of this vector here. Okay, the length being this OE is equal to VM, the maximum voltage here. Okay, now let's use a parallel law and show it here. Okay, now I'm going to draw only this and this. Okay, let's see this now. The same picture here, I just taken here, let's say VL minus VC. Okay, and on this side what happens, we got here VR. Okay, now construct the parallelogram. Okay, and this will give us the resultant voltage here V. Okay, its length will be VM. Okay, now you see from the picture. Okay, and we learned using parallel law also. Okay, this one VM, actually its length will be VM. Okay, so VM square will be equal to what? It will be equal to VR square plus VL minus VC the whole square. Okay, let's see this now. VR square plus this term, that is VL minus, okay, I'll take chalk here, chalk is over. VL minus VC the whole square. Okay, like this way. So how it comes is, we can use a triangle also now. Okay, I can bring this here. Okay, it will become like a triangle. I'll show it to you now. Then erase it now. Okay, that is just for understanding. Okay, so this was this VR. Okay, I turned this picture down. Okay, we got here VM, we got here. Okay, and this part what we got, that is VL minus VC. Okay, so actually this is the hypotenuse. Okay, the square of the hypotenuse is equal to sum of the squares of the other two sides. So you square this term VR square and then VL minus VC the whole square. That's how it comes. Okay, now it's clear. Now let us say go to the next point here. Okay, part here, that is let me erase this phasor here. Okay, now it's enough that we written up to here. Let's draw the phasor. So let us now see this picture here. If it is a picture, let's go to the equation here now. So taking square root, okay. So taking square root on both sides, so what do you get? Okay, that is Vm. When you take square root, that square will go away. Okay, is equal to this side, you get a square root here. That's equal to Vr square plus Vl minus Vc the whole square. Okay, this term we get. Now what we do is, now we have to substitute the values of this Vr, Vl, okay, and Vc. Let's see how to do that now. Okay, so substitute the values, okay, and see now. So what we get is, left side we get your Vm, okay, that's equal to root of Vr square. Okay, Vr square we learned earlier, that is Im into R, okay, the whole square. Okay, this is very important. Remember, you can go through the derivation a little earlier. Okay, plus VL. What is VL? We got that is Im into XL. Okay. Now let's see the next one here. That is minus Im into XC. Okay, that is a capacitive reactance now. This VC we learned this thing. Okay, square. Okay. Now let's see how to solve this. Okay. Well, first thing is I'll change this bracket into square bracket here. Okay. Next step also you can change it, no problem. Okay. If you just leave it, next step from onwards you can change it. Okay, that's equal to root of this one. When you square this, what happens is you will get here Im square into R square. Okay. Plus, see now we have this term now. Okay, like this way. I'll write the square bracket here. Okay. And then we have here Im z now. Okay, I'll take here Im common. So Im is common. So Im into, open a curved bracket here, into XL minus XC. Okay, open close the bracket here, square bracket, and the right square. Okay, now we can easily square it. See, so let's see this now. Root of Im square R square. Okay, plus, now you bring the square inside. Okay, so what do you get here? You get here Im square into XL minus XC the whole square. Okay, it's now simple. Now again you see what is common here. Im square is common, so take it out. Okay, for that, to distinguish, what happens, we'll use a curly bracket here. Okay, so what happens, we get here Im square into, open a curly bracket here, into R square. Okay, plus, now Im square is gone here. So what you get is the curved bracket into XL minus XC whole square. Okay, now when you take square, what happens, Im square, okay, is now this Im will go outside. Let me write on the left side now. I erase this things here, left side. See, I erase the left side. Let's continue now. Okay, here when you take root, what happens is you get here Im, he will go outside, the square terms will go outside, then root of, then we get here R square plus the second term, that is XL minus XC the whole square. Okay, this term will come. And left side, what we have this Vm. That's, we should not forget. Okay, left side we have the Vm. Let me write it. Vm. Okay, now we'll see what's the value of Im here. Okay, so to find the Im, you bring this R square plus this root. Okay, this full term you bring it down. Okay, so what you get is, you get here Vm by root of R square plus XL minus XC, okay, the whole square. On the right side, what you will get? You will get here Im. Okay, rearrange the right. Okay, so on rearranging, let's see what we get here. That is, we will get here Im is equal to Vm divided by root of R square plus XL minus XC the whole square. Okay, the other term should be dropped. Okay, so this value we get here now. Okay, next what happens is, we have to see what is this term here. Okay, so if you see this, it is like this thing here for a resistor. Okay, and we can write it in a different way, or you can write it in another way. That is, Im is equal to Vm by Z. Okay, so this full root term is there now. This full term I can write as Z here. Okay, that's what it is. So what Z is equal to? Z is equal to root of R square plus XL minus XC the whole square. Okay, that will write here. I'll rub the right side now. Okay, then we will continue. Okay, here's the right side now. Let's continue the side here. Okay, this is R. Okay, so In this case we are written here Z is equal to this term now. So where we can say that Z, okay, that is equal to root of this term, that is R square plus this term XL minus XC the whole square. Okay, this is a very important term here that we get here. Okay, the term for Z. Okay, here Z is called as a thing that is called as a impedance. Okay, it's called as impedance. Okay, we call this as impedance. Be very careful spellings here. Impedance. Okay, some new terms that we learn. Okay, it's kind of resistance only, but happens only in a AC circuit. Okay, we should not write resistance. Okay, resistance is for DC circuit, but here we call it as impedance. Okay, so this impedance means what? It is equal to root of the resistance square plus the inductive reactance and minus the capacitive reactance. Okay, so these are the terms you know. Okay, next we'll see this one, that phase diagram will go again. Okay, so we saw the phase diagram, we got this way, that is VR. You can refer the phase diagram. VR was here, and then this side we had this VL minus VC. Okay, do you remember this? Okay, then we use a param law like this way, and then we got the resultant voltage, that is VM, like this way. Okay, here we go. Now next what we do, we have to take this thing and use a triangle law now. Okay, so how to use a triangle law? So I will take this VR down. Okay, so using triangle law now. Okay, we use a triangle law of vector addition. Okay, so VR is down here. VR first is we saw now. Then VM. Okay, VM is here. Okay, then VL minus VC. I'll take this side here. Okay, so this topic will come as VL, or this part is the phasor is VL minus VC. Okay, and this angle, we say that angle is phi. Okay, phi is called as a phase angle. Okay, PHASC. Okay, don't think phase PHASC. Okay, now from this picture we'll see what is tan phi equal to. Okay, tan theta, that is equal to what? Opposite side by the adjacent side. So opposite to this is VL minus VC. It's a triangle now. So we have here VL minus VC by the adjacent side, that is VR. Okay, adjacent side is VR here. Okay, next what we do is substitute the values here again, very simply. So substitute the values. Okay. Let's substitute the values and see. Okay, so before that I have to erase the left side now. Okay, let me erase it down. So I have rubbed the left side here. Okay, let's substitute the values and see now. Okay, so when you substitute the values here, instead of this VL, okay, so what is VL equal to? That's equal to IM into XL. Okay, same way, minus VC, that is IM into XC, that is the capacitive reactance, divided by VR, that is IM into R. Okay, now you see the numerator, that is IM is common, so take IM out. So IM into XL minus XC. Okay, divided by the denominator we have here IM into R. So IM and IM will cancel. Okay, so what do you get here? We get here that is XL minus XC divided by R, and that's left side is tan phi. Okay, so tan phi you get. Okay, so this is a thing here. From this we can find the phase angle. Okay, let me put a cloud this. Okay, this is also a very important relationship. Okay, so this will help us to find the phase angle. Now from this equation what we understand, okay, some things, some special case we have, that I erase this right side and then we'll write down. Okay, let us now see the special cases here. Special cases. Okay, in this expression here. So using this. Okay, so first one we see, if this XL is more than XC. Okay, that is the inductive reactance is greater than the capacitive reactance. Okay, you put more coil there. Coil is having much more bigger value than the capacitance. So let's see what will happen. Then if this value, then what will happen? If this bigger means XL minus XC will be positive. Okay, we see that XL minus XC will be equal to, it's positive. Okay, it's a positive term. Then the phase angle you see. Okay, the phase angle, that's this phi. Okay, will be also be equal to positive. Okay, phase angle phi here. Phi I didn't write. Okay, how to find phi? You write tan. This tan inverse will come now. It's simple. Okay, that will be positive term. And then you see next what happens is the applied voltage will lead the current by 5 degrees. Okay, so applied voltage leads the current by 5 degrees. Okay, taken this chalk here, leads current by 5 degrees. Okay, and then we know the equation here, that is V is equal to Vm sine omega t. Okay, this was the voltage that we give, and now let's write the value of current here. You see, voltage leads now. Okay, so current will lag behind. Okay, so Im sine omega t, okay, minus 5. Okay, so this is minus sign. Why? Because we say voltage leads the current by 5. Okay, so current is less by 5 now. Okay, that's clear. Okay, now let's go to the second special case here. Let me rub out this and we'll go to the second special case. So the first special case is over. Let's go to the second one. So let us go to the second special case from this thing. Okay, from this thing equation here. So second special case, that is the opposite of this. If Xc, the capacitive reactance, is more than the inductive reactance. Okay, if Xc, okay, or else we can say one more way. If the inductive reactance XL is less than the Xc, okay, this is less, okay, this is more. Okay, what will happen? Okay, then we see that this thing, that is XL minus Xc. Okay, this is less and this is more now. So what happens? It will become a negative value. We will get a negative value. Okay, and the phase angle, if you see, okay, the phase angle phi, that also will be negative. Okay, that also will be negative because tan inverse of minus quantity will get. Okay, so the minus will go outside, so we'll get a negative value only. Okay, phase angle. And now you see the current will lead the voltage by phi. Okay, the current is more. Okay, current will lead the voltage. Current will leads the voltage by phi. Okay, current leads the voltage by 5 degrees. Okay, so and now you see the circuit here will be capacitive. Okay, circuit is capacitive. Okay, I forgot to write the first one, that is, you see, circuit was inductive that case. Okay, for first special case, circuit was inductive. Now in this case, the circuit is capacitive because we have Xc is more now. Okay, and then we write the value for the voltages here. The equations, V is equal to again Vm sine omega t. This we know already. Okay, but now you see current here. Current I is equal to Im into sine of omega t. Okay, sorry, this bracket will not come here. This side will come. Okay, sine of omega t plus phi. Why? Because the current leads the voltage now. So current will be leading it by phi. So that's why it can plus sign. Okay, so this is for the second case here. If the inductive reactance less, okay, than the capacitive reactance. Okay, so let me go to the third case here. I'll erase this right side now. Okay, let's now go to the third case here. Okay, third case. What will be third case here? XL will be equal to Xc. Okay, the inductive reactance. Okay, if the inductive reactance, that is XL, is equal to the capacitive reactance, that is Xc. Okay, both are equal. Then what will be the phase angle? Both are equal means it will come 0 now. So the angle phi also will be 0. Okay, so then the phase angle phi is equal to 0. Okay, and then what you can say, the current and the voltage are in phase. Okay, so current and voltage are in phase. Okay, so we learned that for which circuit the current and voltage are in phase? For resistive circuit only. AC circuit containing a pure resistor. We learned earlier now. So we can say the circuit is resistive. Okay, the circuit is resistive. Okay, that's only the resistance will be contributing to the losses of current here. Let me take the chalk here. Now let's write the value for the voltage and value for current here. So value for voltage, that is V is equal to Vm sine omega t. Okay, we know this. Then current here, I is equal to again Im sine omega t. I did not write plus phi or minus phi. Why? Because we say current and voltage are in phase. So this angle and this angle will be equal. Okay, you see this now. Okay, so this is about the circuit which contains inductor, capacitor and resistor in series. We can say series LCR circuit. Okay, so go through the equations here, write once or twice. Please understand the concept there. Okay, go through the video one or twice, 2 times. Okay, thank you for watching.